The transport truck's diesel engine coughed to silence. November 15th, 1943, Aberdeen Proving Ground, Maryland. 34 degrees and falling fast. Staff Sergeant Mike Kowalski pulled his collar tighter against the wind, cutting across frozen testing grounds like a knife through sheet metal. 15 years on Detroit assembly lines had taught him to read machines the way other men read books. He knew Ford. He knew Chrysler. He knew American steel and American horsepower. What he didn't know was sitting under that olive-drab tarp, 1,740 pounds of enemy engineering that every mechanic at Aberdeen expected to be automotive perfection wrapped in German precision. The Kübelwagen emerged as they pulled back the covering. Even motionless on Aberdeen's concrete pad, it possessed an elegance that made nearby American Jeeps look crude by comparison. Clean lines, sophisticated design, the kind of machine that looked like it belonged in a museum, rather than a war. This was supposed to be German engineering supremacy on four wheels. The Wehrmacht's answer to the American Jeep. Intelligence photographs had shown these vehicles carrying officers across conquered Europe. Tactical reports from North Africa described their battlefield mobility. Even sitting here in Maryland's bitter cold, the Kübelwagen radiated confidence of a machine built by people who understood precision. Technical Sergeant James Patterson approached from the dynamometer building. 5 years at General Motors had taught him methodical precision, his breath visible in November air as he carried a clipboard thick with testing protocols. The brass wants the complete treatment, he announced. Full technical analysis for manual TME 9803. Everything from power curves to maintenance requirements. War Department needs comprehensive data about enemy equipment capabilities. Kowalski nodded, his calloused hands already reaching for the hood release. This was more than another testing assignment. This was his chance to measure American industrial muscle against the vaunted German engineering tradition. Every American mechanic knew the Germans built the best cars in the world. Mercedes, BMW, Volkswagen, names that represented automotive excellence that Detroit secretly envied. The hood lifted with a satisfying mechanical click. Kowalski stared, his expression shifting from anticipation to confusion to something approaching disbelief. The power plant, nestled between the frame rails, looked more like something from a civilian economy car than military equipment. Air-cooled cylinders arranged in a flat configuration. Minimalist in construction. Almost delicate compared to robust cast-iron blocks he knew from Detroit assembly lines. He checked the specification sheet once, then twice, then a third time, because the numbers couldn't possibly be correct. 25 horsepower. The German wonder weapon produced 25 horsepower from its tiny air-cooled engine that looked more like a lawnmower, motor than military equipment. The American Willy's Jeep, sitting 50 yards away, produced 60 horsepower, more than twice the output of this German machine. Even the ancient Ford Model A that his father had driven through the Depression generated more power than this supposed masterpiece of Wehrmacht engineering. Kowalski felt something shift in his understanding of the war. If German engineering wasn't superior, then why were American boys dying in European mud? Why was the Wehrmacht still winning battles if their equipment was this inadequate? The questions hung in cold Maryland air like accusations waiting for answers. Corporal Tommy Chen appeared beside them, slide rule already in hand, with practiced efficiency of someone who spoke mathematics as a native language. Berkeley engineering degree, making him the team's resident genius. Displacement 985 cubic centimeters, he announced. His calculations transforming German metric specifications into numbers American mechanics could understand. That's about 60 cubic inches, peak power at 3,300 RPM. Power to displacement ratio is terrible. Worse than most civilian vehicles we've tested. Worse than economy cars built for fuel efficiency rather than performance. Patterson made careful notes, his engineering background demanding documentation of every observation. This wasn't just mechanical curiosity. American commanders were making tactical decisions based on assumptions about German technical superiority. If those assumptions were wrong, The implications stretched far beyond automotive engineering into questions about why the war was being fought the way it was being fought. Why casualties were so high if enemy equipment was this limited. Major Robert Sterling arrived as the team began preliminary inspection. Pressed uniform and polished brass, marking him as institutional military establishment. 20 years of service teaching him to respect European military traditions. "Gentlemen," he announced with formal courtesy that barely concealed his own curiosity. This evaluation carries significant strategic importance. German automotive engineering has long been considered among the world's finest. We need to understand exactly what advantages their equipment provides on the battlefield. Kowalski bit back his first response. Years of military discipline overriding working-class instincts. The Major's expectations were clear. They were supposed to find evidence of German technical superiority. But the evidence sitting before them told a completely different story. This wasn't the automotive masterpiece that intelligence reports had suggested. This was a compromise, elegant in some ways perhaps, but fundamentally limited by design. Choices that prioritize theory over practical, battlefield performance. The engine's construction revealed design philosophy that prioritized different values than American automotive engineering. Where Detroit built for power and durability, Germans had optimized for fuel efficiency and manufacturing simplicity. The air cooling system eliminated weight and complexity of liquid cooling, but at the cost of thermal management under sustained stress. As afternoon shadows lengthened across Aberdeen's testing grounds, Kowalski found himself staring at a machine that challenged everything he'd believed about German engineering supremacy since the war began. The real evaluation would begin tomorrow, when dynamometer measurements would replace subjective impressions with hard numbers that couldn't be argued with. The Emperor's new car was sitting before them. The dynamometer building hummed with electrical energy as Patterson fired up the massive testing apparatus. 4 days of preparation had transformed Aberdeen's primary automotive testing facility into a precision measurement laboratory. Cables snaking across concrete floor like mechanical arteries connecting German engineering to American scientific methodology that would strip away assumptions and reveal mathematical truth. The morning air carried sharp scent of industrial lubricants and electrical equipment, familiar aromas that reminded Kowalski of Detroit proving grounds where peacetime automotive dreams had once been tested. Beginning baseline power measurement, Patterson announced, his voice carrying methodical tone of someone who understood that sloppy data undermined credible conclusions. The War Department demanded a number that could withstand scrutiny from Pentagon engineers who had never seen combat but possessed absolute faith in quantified analysis. The Kübelwagen's engine note changed as Patterson gradually increased dynamometer load, simulating resistance of hills, headwinds, and battlefield conditions. At idle, the flat-4 engine produced a distinctive sound, smoother than American inline configurations perhaps, but somehow less substantial. Like a sewing machine compared to a bulldozer. Chen positioned himself beside the instrument panel, slide rule ready. His Berkeley engineering education, providing mathematical framework needed to translate raw measurements into meaningful comparisons. Peak torque at 2400 RPM, he called out, recording figures that would soon travel to Washington in classified reports. Maximum power output 25.3 horsepower at 3,300 revolutions per minute. The implications hit Kowalski like cold water. Those weren't preliminary estimates subject to measurement error. They were precise calculations of German automotive engineering at its theoretical peak performance. The Kübelwagen was performing exactly as designed, delivering every horsepower that Volkswagen's engineers had promised. The problem wasn't mechanical failure or poor maintenance. The problem was that German engineering had optimized for entirely different priorities than American automotive design philosophy that valued raw power above theoretical elegance. Patterson's stopwatch clicked as they began acceleration tests. 26 seconds elapsed before the speedometer needle reached 30 miles per hour, a performance that would have been embarrassing for a civilian passenger car. much less a military vehicle designed for battlefield mobility, where speed often meant survival. The nearby Willy's Jeep could complete the same acceleration test in 11 seconds, reaching 30 with authority that spoke of Detroit's commitment to excess capacity and mechanical power. Weight comparisons shows interesting trade-offs. Chen announced, Kübelwagen weighs 1,740 pounds versus the Jeep's 2,453. They save 700 pounds of structural mass through lightweight construction, but the power-to-weight ratio still favors American engineering by a significant margin. Raw horsepower advantage more than compensates for additional vehicle weight. Major Sterling observed from the building's observation deck, his military bearing unable to completely mask growing concern about what these measurements revealed. 2 decades of service had conditioned him to respect European military traditions, but the numbers emerging from Aberdeen's testing facility challenged fundamental assumptions about German technical superiority. If Wehrmacht vehicles possessed inferior performance characteristics, how did German forces maintain tactical advantage across multiple theaters of operation? The cooling system evaluation produced the most troubling results. Patterson monitored engine temperatures as dynamometer load increased, watching thermal indicators that would have triggered immediate shutdown procedures for any liquid-cooled American engine. The air cooling system's limitations became apparent at sustained high-power output, thermal management that worked adequately under normal civilian driving. Conditions began failing catastrophically when military requirements demanded continuous high-stress operation, temperature rising beyond acceptable parameters at sustained 22 horsepower output, Patterson reported, his engineering background providing context for measurements that revealed fundamental design limitations. Thermal stress indicators suggest this power plant cannot maintain military performance standards under combat loading conditions. Any sustained operation at high power will result in thermal failure and mission-killing mechanical breakdown. Chen's slide rule moved with practiced efficiency as he calculated thermal efficiency ratios. The mathematics revealed uncomfortable truths about engineering compromises that looked elegant in design studios but failed under battlefield stress. Heat dissipation inadequate for sustained military operation, he concluded, his numbers confirming what Kowalski's mechanical instincts had already suspected. Every number told the same story. American automotive engineering had achieved superior performance through different design philosophy that prioritized power and durability over theoretical elegance. Aberdeen's hill-climbing course stretched across the Proving Ground's eastern sector like a geometric challenge to automotive engineering. Its 12-degree gradient, representing the kind of terrain that separated capable military vehicles from automotive pretenders. The morning air carried frost that would soon give way to mechanical heat of engines pushed beyond their comfort zones. Patterson had positioned temperature monitoring equipment at strategic points along the route, creating a comprehensive measurement system that would document exactly how German air cooling performed under sustained load conditions. Kowalski engaged first gear and felt the Kübelwagen begin its assault on Aberdeen's artificial mountain, the flat 4 engine note changing from conversational idle to labored protest as gradient physics demanded more power than Volkswagen's engineers had provided. At the 500-foot mark, engine temperature gauges began registering thermal stress that would have triggered warning protocols in any liquid-cooled American vehicle. The air cooling system's fan howled with mechanical desperation, trying to dissipate heat that accumulated faster than aluminum fins could release it to Maryland's cold November atmosphere. Chen monitored the vehicle's progress through binoculars, his slide rule calculating real-time power requirements against observed performance degradation. Mathematics revealed the cruel efficiency of physics that cared nothing for engineering elegance. Every degree of incline multiplied the engine's workload exponentially, transforming the Kübelwagen's marginal 25 horsepower into woefully inadequate motivation for climbing even modest hills. Speed dropping below 15 miles per hour, he called out, his voice carrying across the testing ground with clinical precision. Engine temperature exceeding normal operating parameters. Vehicle approaching thermal failure under conditions that represent routine military requirements, rather than extreme operational stress. The Kübelwagen's transmission began hunting between second and third gear as Kowalski fought to maintain forward momentum against gravity's relentless mathematical certainty. German engineering had optimized for fuel efficiency under peacetime assumptions, but battlefield mobility demanded sustained power output that the air-cooled engine simply could not deliver without thermal distress that threatened catastrophic mechanical failure. At the 800-foot mark, temperature indicators entered the danger zone, where mechanical failure became inevitable rather than merely possible. Temperature now at 210 degrees Fahrenheit, Patterson reported. Recommend immediate shutdown to prevent engine damage that will render vehicle non-operational. But Kowalski pressed forward, understanding that this test represented more than automotive evaluation. It was measuring whether German engineering's superiority was real or merely assumed. The engine's mechanical protests grew more desperate as aluminum pistons expanded beyond design tolerances, creating clearances that reduced compression and further degraded power output in a cascading failure mode. Steam began rising from the engine compartment as lubricating oil approached temperatures where molecular breakdown would destroy the engine's ability to protect itself against friction. Major Stirling watched from the observation bunker as the vehicle that represented German automotive achievement struggled up a hill that delivery trucks climbed daily without mechanical distress. His military education had emphasized respect for European engineering traditions, but the evidence unfolding before him challenged assumptions that had shaped American strategic thinking since the war began. At 900 feet, the Kübelwagen finally surrendered to physics and engineering reality that no amount of theoretical optimization could overcome. Kowalski felt power output collapse as thermal stress overwhelmed the engine's ability to convert fuel into mechanical motion, leaving him coasting backward down the hill, while German precision engineering vented superheated air through every available opening. The vehicle that intelligence reports had described as militarily capable had failed a test that represented routine battlefield requirements. The comparison test with an American, Willy's Jeep, provided stark demonstration of engineering philosophy differences. The Jeep attacked the same 12-degree gradient with mechanical confidence that spoke of Detroit's commitment to excess capacity. Where the Kübelwagen had struggled and failed, the American vehicle climbed with power reserves, sufficient for even steeper grades under full combat loading with additional safety margin. Chen's calculations revealed the mathematical reality behind observed performance differences. Maximum sustainable grade for the German vehicle appears to be 8 degrees under load. He announced, American Jeep capability extends to 27 degrees under identical loading conditions. Power-to-weight advantage translates directly into operational mobility superiority that provides tactical flexibility. The traction testing provided final humiliation as Kowalski guided the rear-wheel drive Kübelwagen into Aberdeen's sandpit. 4 inches of loose sand, barely enough to challenge a civilian passenger car, proved sufficient to immobilize the German vehicle completely. Its narrow tires and rear weight bias created a combination that transformed minor terrain obstacles into mission-killing mobility constraints. The same sand trap that stopped American Jeeps at 18 inches had defeated German engineering at 4 inches. Aberdeen's maintenance bay echoed with precise sounds of systematic disassembly as Kowalski approached the final phase of evaluation. December's bitter cold had transformed the unheated workshop into an environment that simulated harsh conditions where combat mechanics would struggle to keep vehicles operational. The routine oil change began what Patterson had designated as comparative maintenance analysis, timing every procedure against identical operations on American equipment to quantify hidden costs of design complexity. Kowalski's stopwatch started as he located the Kübelwagen's oil drain plug, immediately discovering that German engineers had prioritized theoretical elegance over practical field service. The drain point was positioned behind a protective skid plate that required tool access from multiple angles. transforming a simple operation into an exercise in mechanical contortion. 15 minutes elapsed, and we haven't drained a drop yet, Kowalski muttered, his breath visible in the cold air as he wrestled with access panels that seemed designed by engineers who had never changed oil under battlefield conditions. 15 years of Detroit assembly line experience had taught him that maintenance complexity was the enemy of operational availability. Every extra minute spent servicing vehicles was time that reduced combat effectiveness. Patterson documented each step with methodical precision. German design philosophy appears to prioritize component protection over service accessibility, he observed. The oil change that consumed 12 minutes on an American Jeep required 45 minutes on the Kübelwagen. With most of the additional time spent accessing components that German engineers had buried beneath protective covers, Chen calculated the tactical implications with slide rule precision. Maintenance time differential represents 27% reduction in unit availability during sustained operations, he announced, his mathematics revealing how design choices affected combat effectiveness through logistical constraints rather than mechanical performance. Units spending more time on maintenance meant fewer vehicles available for combat operations. Spark plug replacement provided even more dramatic evidence of German engineering priorities. The Kübelwagen's horizontally opposed engine configuration buried the spark plugs beneath cooling shrouds and electrical components that required partial engine disassembly to access. What should have been an 8-minute procedure became a 35-minute mechanical archaeology expedition. "This is insane," Kowalski said, holding a spark plug that had required removing 6 separate components to reach. Any farm mechanic in Iowa could service a Jeep engine with a basic toolkit in the field. This thing needs a complete workshop and half a day just to change plugs. His working-class pragmatism rebelled against design, complexity that served no practical purpose except demonstrating engineering sophistication. The cold start testing on December 8th provided final confirmation of German engineering limitations. At 10 degrees Fahrenheit, typical European winter weather, the Kübelwagen's engine refused to start despite 6 attempts with proper starting procedures. The air cooling system that eliminated liquid coolant freeze problems created carburation and ignition, difficulties that made cold weather operation unreliable. Kowalski watched the American Jeep fire immediately under identical conditions. Its liquid-cooled engine and robust electrical system demonstrating design priorities that favored operational reliability over theoretical efficiency. "Game over," he announced, understanding that these measurements represented more than automotive comparison. They revealed fundamental differences in engineering, philosophy that would determine which industrial system could sustain military operations. December 15th arrived at Aberdeen with bitter cold that transformed metal into ice. Kowalski sat in the empty maintenance bay, staring at his completed technical report, while outside the wind howled across Maryland's frozen landscape. Every number in technical manual TME 9803 told the same uncompromising story. American automotive engineering had achieved measurable superiority over German design in every category that mattered. 25 horsepower versus 60, 45-minute oil changes versus 12 minutes, hill climbing failure at 8 degrees versus 27-degree capability, cold start failure at 10 degrees Fahrenheit, traction failure in 4 inches of sand. The mathematics were irrefutable. But American soldiers were still dying in Italian mountains and French hedgerows, still struggling against Wehrmacht forces equipped with vehicles that Aberdeen's testing had proven inferior to American industrial production in every measurable way. The contradiction gnawed at Kowalski's working-class logic like a mechanical problem that refused to yield to conventional diagnostic procedures. If German equipment was this inadequate, why weren't American forces winning decisively instead of fighting yard by yard through terrain that seemed to favor defenders equipped with demonstrably inferior hardware? Patterson found him there after midnight, the former General Motors engineer carrying 2 cups of coffee and the weight of his own professional confusion. "Numbers don't lie," he said. settling into a chair beside the workbench where months of measurement data lay arranged in neat piles. But they don't explain why Wehrmacht units maintain operational effectiveness despite equipment limitations we've documented with scientific precision. Chen joined them around 0300. His slide rule, forgotten as mathematical precision, gave way to broader understanding of how warfare actually functioned when human factors combined with mechanical capabilities to produce tactical outcomes that transcended simple equipment. Comparisons. "We've been measuring the wrong variables," Patterson said, his engineering background providing framework for analysis that extended beyond horsepower specifications. German forces aren't winning because their vehicles are better. They're winning despite having worse vehicles because of superior doctrine, training, and tactical integration that maximizes limited mechanical capabilities through methods we haven't learned yet. The insight struck Kowalski with the force of mechanical revelation, transforming months of testing data from confusing contradiction into coherent explanation. German units succeeded because they understood how to extract maximum capability from limited resources through tactical methods refined over years of combat experience, while American forces were still learning how to integrate superior equipment into effective tactical systems that could translate material advantages into battlefield success. Major Sterling discovered them there at dawn. 3 men surrounded by documentation that had evolved from simple automotive evaluation into strategic analysis of why equipment advantages didn't automatically translate into battlefield success without proper doctrine and training. German engineering wasn't superior, Kowalski said, articulating insights that months of testing had gradually revealed. It was just different, optimized for mass production under resource constraints rather than performance maximization that American industry could achieve. They're fighting a poor man's war with equipment designed for efficiency rather than capability. And they're winning because they understand how to use limited resources effectively through tactical methods we haven't mastered yet despite our superior equipment. The implications extended far beyond Aberdeen's testing protocols into strategic questions about how American industrial might could be translated into tactical advantage on European battlefields. Superior equipment meant nothing if operators lacked training, doctrine, or experience necessary to exploit technological advantages under combat conditions. Patterson began drafting supplementary analysis that would accompany Technical Manual TME 9803 to Pentagon briefing rooms, explaining how German tactical success despite equipment inferiority revealed the importance of training, doctrine, and operational experience in determining battlefield outcomes. American forces possessed superior vehicles, weapons, and logistical support through industrial capacity that Germany couldn't match. But Wehrmacht units maintained tactical effectiveness through superior integration of limited resources into coherent operational systems refined through years of combat experience. Chen's mathematical models revealed the strategic implications of Aberdeen's discoveries, calculating how American equipment advantages would eventually overcome German tactical superiority as Allied forces gained operational experience, while Wehrmacht units exhausted their trained personnel and logistical infrastructure. The war would be won by industrial capacity rather than individual equipment superiority, with American mass production overwhelming German efficiency through sheer quantitative advantage. As morning light filtered through Aberdeen's windows, the team understood they had documented more than automotive comparison. They had revealed fundamental differences between American and German approaches to military technology that would determine the war's ultimate outcome. German engineering represented sophisticated optimization under resource constraints that prioritized efficiency over raw capability, while American production demonstrated industrial capacity that could overwhelm efficiency through massive quantitative superiority. On June 6, 1944, as 16,000 American jeeps rolled onto Normandy beaches carrying soldiers trained to exploit their equipment superiority through doctrine that had learned from German tactical success, Kowalski's technical manual provided mathematical confirmation of what D-Day would demonstrate operationally. American industrial might, properly applied through effective tactics, refined through hard-won combat experience, would prove decisive against German efficiency constrained by limited resources and increasingly desperate strategic circumstances. The Kübelwagen remained at Aberdeen for months after that initial evaluation, becoming a teaching tool for mechanics who would deploy to Europe with knowledge that enemy equipment wasn't invincible, that German engineering could be understood, measured, and overcome through systematic analysis, rather than feared as some mystical Teutonic superiority. Technical Manual TME 9803 traveled to every American motor pool in the European theater. Dog-eared copies appearing in field workshops from Italy to France to Germany itself. The manual became something more than technical documentation. It became proof that American industry had created not just superior equipment, but a systematic approach to warfare. Kowalski never saw combat himself. His war was fought in maintenance bays and testing facilities where mathematics replaced bullets and measurement replaced courage. But the intelligence reports that filtered back from Europe confirmed what Aberdeen's testing had predicted. Wehrmacht mobility was collapsing under the weight of mechanical failures that inadequate maintenance and resource shortages made inevitable. The elegant Kübelwagen that looked so sophisticated on parade grounds was breaking down on European roads at rates that German logistics couldn't sustain. All the limitations that Aberdeen had documented were destroying German tactical mobility, regardless of the superior doctrine. By winter of 1944, captured German documents revealed Wehrmacht quartermaster reports painting a picture of mechanical collapse. Units reporting 50% vehicle availability, mechanics cannibalizing multiple broken vehicles to create one functional machine. American Jeeps, meanwhile, were performing exactly as Aberdeen's testing had predicted, crude perhaps by German engineering standards, but functionally superior in every measurable way when battlefield conditions demanded reliability, maintainability, and sustained performance under stress. Patterson received letters from mechanics in the field, men who had trained at Aberdeen, and deployed to Europe with knowledge that transformed how American forces approached enemy equipment. One letter came from a motor pool sergeant in the Ardennes. December 1944. Battle of the Bulge, raging around his position. "We captured 3 Kübelwagens yesterday," the sergeant wrote, "just like your manual said. 2 wouldn't start in the cold. The third made it half a mile before the engine overheated climbing a hill. Meanwhile, our Jeeps are running 24 hours straight in weather that should stop everything. Your testing saved lives by teaching us we had better equipment than the enemy." The testing facility at Aberdeen continued operating long after Germany's surrender, evaluating captured equipment from every theater of the war. The methodology that Kowalski, Patterson, and Chen had refined became standard practice for American military evaluation of foreign equipment, a legacy that extended far beyond one German vehicle into systematic approaches to understanding enemy capabilities that shaped Cold War intelligence gathering and military procurement decisions for decades. Kowalski returned to Detroit after the war, back to assembly lines where his mechanical expertise shaped automotive production during America's greatest industrial expansion. He never spoke much about his service, never claimed credit for insights that had traveled to Pentagon briefing rooms and shaped strategic decisions. But sometimes, watching cars roll off production lines with the same systematic precision that had characterized Aberdeen's testing protocols, he thought about that cold November day when a German vehicle had arrived carrying assumptions that mathematics had systematically dismantled. The lessons stayed with him. That engineering was about solving practical problems rather than demonstrating theoretical sophistication. That elegant designs meant nothing if they couldn't survive real-world abuse. That warfare's outcome was determined by complex factors that transcended simple equipment comparisons. The Kübelwagen had been a teacher despite itself. revealing uncomfortable truths about how propaganda could substitute for analysis, how mythology could obscure reality, how systematic measurement could strip away assumptions to reveal practical truth. Patterson stayed in military service, rising through ranks to become one of the Army's senior automotive engineers during the Cold War era. He established testing protocols that became standard across all military branches, ensuring that future evaluations would approach foreign equipment with the same rigorous methodology that had revealed the Kübelwagen's limitations. Chen returned to Berkeley, completing his engineering degree and eventually joining the faculty where he taught generations of students about the importance of systematic measurement over cultural assumptions. The Kübelwagen became a case study in his classes, an example of how mathematics could reveal truths that propaganda obscured. The war in Europe ended on May 8, 1945. Victory in Europe Day. Celebrations erupting across American cities and European battlefields. The jeeps that had carried men from Normandy to Berlin bore scars of battles won and lost, but they were still running, still functional, still demonstrating every day the practical superiority that Aberdeen's testing had documented through careful measurement that stripped away mythology to reveal mathematical truth. The contrast told its own story, about how wars were won, not by elegant engineering, but by systematic industrial production, combined with tactical doctrine that maximized equipment capabilities through training and experience. About how assumptions were dangerous and measurement was necessary. About how mythology could obscure reality until careful analysis revealed the truth that determined whether nations survived or fell. About how sometimes the crude and powerful defeated the elegant and sophisticated simply by refusing to break. When conditions demanded sustained performance under stress, Technical Manual TME 9803 remained in circulation for decades after the war, becoming a reference document for military historians studying how American forces had overcome initial tactical disadvantages through combination of superior equipment and improving operational methods. Future generations of military planners studied Aberdeen's methodology, learning that understanding enemy capabilities required systematic evaluation rather than accepting assumptions based on propaganda or cultural prejudice. The legacy of that cold November day in 1943, when a German vehicle arrived at Aberdeen carrying assumptions that would be systematically dismantled through scientific measurement, extended through decades of American military thinking, shaping how forces approached foreign equipment evaluation, how planners assessed enemy capabilities, how doctrine was developed to maximize American advantages while exploiting enemy weaknesses, revealed through testing, rather than assumed through cultural prejudice. The Kübelwagen had taught that warfare's outcome was determined by factors more complex than simple equipment comparisons, that material advantages required proper tactical application to translate into battlefield success, that understanding enemy capabilities demanded careful measurement rather than accepting mythology as substitute for analysis. The wind still blows across Aberdeen. Proving ground. Testing facilities still evaluate equipment through protocols descended from methodology that Kowalski, Patterson, and Chen refined during those cold months in 1943, when they systematically dismantled German engineering mythology through careful measurement. The story of the Kübelwagen wasn't really about a vehicle. It was about assumptions challenged and mythology dismantled and truth revealed through systematic measurement that didn't care about cultural prejudice or propaganda from either side. It was about how wars were won, not by elegant engineering alone, but by industrial capacity, combined with improving tactical doctrine that learned to exploit material advantages through combat experience. It was about how young men lived or died, based on decisions made in testing facilities where mathematics replaced courage and measurement replaced bullets, but the consequences were just as real as any battlefield. Long after the last veteran died, and the last Jeep was scrapped and the war became history rather than memory, the lesson remained. That systematic analysis was more valuable than assumptions. That careful measurement revealed truths that propaganda obscured. That understanding enemy capabilities through rigorous testing was essential for victory in conflicts where industrial might and tactical sophistication combined to determine which nations survived and which fell. The Kübelwagen had taught all of this through its failure to meet expectations, through limitations exposed by testing that stripped away mythology to reveal practical reality, through lessons learned in Maryland's cold that saved lives on European battlefields where American boys drove vehicles that weren't theoretically perfect, but were practically superior in every way that mattered when metal met mud and assumptions met mathematical truth.